So this is the third question in the mixed pure support step 3 booklet. It's 2009 question number 8. It's all about limits and then some integration with some reduction formulas at the end. So that's cool. And we're going to start here by using this to show this thing here. So we'll start obviously with this left-hand side there, I guess, and we'll make this substitution. Now, the reason we're going to make this substitution is because we can notice that, like, ideally, we just want t to be log of x, I guess, looking at these two parts here and comparing. But if t was just log of x, then as x goes to 0, t goes to negative infinity, not to infinity. So I think we need a negative in there as well to balance that out, and then just hope that we can fix that later. But it's pretty important that we get this bit started right. So let's just go ahead and make this one here instead. Of course, when we put in the x is e to the minus t here, so that's going to be that out there, and then this just gets replaced with that there. So this is okay. This obviously makes this work as well, so that's all good to go. We're pretty much going well. It's just this minus t that isn't so good, but we can just factorize out a minus 1 n times from that to leave this. And because that doesn't depend on t, this last term here, we can just bring it out to the front of the log. And because this whole thing goes to 0, which we're apparently allowed to just use, then this becomes 0, and it doesn't matter whether it's being times by 1 or minus 1 or anything else. So that would just be 0 there, and we'll be good to go. Then it says by writing this, show this thing here. So, okay, well, we'll do that. We'll start with the left-hand side, writing this like this here. And now if you did the preparation section for this question, it would be very helpful because you could know that if you have a function of some x's here, you can put the limit on the inside of that function there, like so, like this, which is really useful because this is just the result we just did where m and n are both 1. But this didn't depend on what n or m were. So we can just say that and we can send it to 0, and e to the power 0 is 1. So therefore, this is 1 as required. Now we get to the integration section. Okay, we have this thing here, and we're showing this here. Now, if you've done the reduction formula sections of A-level further maths, you'll find this, I think, quite nice. We'll obviously start with in plus 1, like this, and usually when you do this, it's about doing integration by parts in order to try and get down to the lower integral so you can write them together like this. Let's do integration by parts. Let's integrate the one we can integrate, which is x to the m. That integrates to x to the m plus 1 over m plus 1, and leave the other function alone, and evaluate that between between the limits 1 and 0. And then we take away, keep integrating this one, but then differentiate this one. If you do integration by parts differently to how I've just explained it, where it just goes integrate, leave alone, differentiate, then go ahead and do it your own way. But this is just how I do it. Of course, this works out nicely because this 1 over x cancels with one of these x's to leave x to the power m. We can factorize out this n plus 1 thing here, which is great, because that's obviously there. Now this here, we need to evaluate. When you put in 1, log of 1 is 0, so the first term goes away. When you put in 0, I believe this is what this proof was for here. We can't really put 0 into log of x, but what we can do is we can say the limit as our input approaches 0 of of 0 to some number times log of 0 is equal to 0 with some other power that we still don't really care about. So this, by this result here, is going to be just 0 minus 0, which is very nice of it. And like I said, we can do some stuff over here. And now this here, I think, is just perfectly in. So we end up with in plus 1 equals what was desired. So that's all good. Now it says hence evaluate in. Now, we obviously can't do that unless we know what n is. So the answer is going to be in terms of n. Now, there is one that we can evaluate, which is I0. Which is quite easy to evaluate, right? Because I0 is just what happens when you put in 0 here, which looks like this. And we can just, of course, this is just 1, so we can just integrate x to the m, which is x to the m plus 1 over m plus 1, put in 1, 0, and we end up with 1 over m plus 1. So that's quite useful. But how do we use that when we're trying to evaluate in and we don't have a connection between in and I0? Well, what we can do is we can use this result here to say this result instead. So all I've done there is I've replaced n plus 1 with just n. So in is, and we reduce this by 1, reduce this by 1, reduce this by 1, and I think we end up with this expression here. So that's just this expression here. Again, just replacing the n's with n minus 1s, I guess. And we end up here. But the thing is, we can just do that again with in minus 1. Right, in minus 1, replace the n's with n minus 2s, and this will become a minus 1, and that will become a minus 2. And then we can do that again, and we can do it again. And we can keep doing it all the way down to I0. And now all we have to do is firstly substitute the result we know for I0, which is 1 over n plus 1, but also just count carefully everything that's going on here to try and come up with a neat expression for in. So, well, okay, looking at the tops here, we've got n times n minus 1 times n minus 2 all the way down to 1. So that's just n factorial, so that's fantastic. What about all the minuses? Well, how many minuses are there? There's a minus for every single one of these from n minus 1 down to 0. Now, counting things from 0 to n minus 1, I think that means that there's n of them, because there's n things from 1 to n. So therefore, there's n things from 0 to n minus 1, because you've added a 0 but taken away an nth term. So I think there are n minus 1s, and I think there are also, for exactly the same logic, n m plus 1s on the bottom. There's just going to be the same number of those as there are minuses, clearly. So I think we end up with this, the n factorial I explained before. And of course, I can substitute in this I0 result, which just increases the power of this bracket here. And I think this would be a result that we could, I guess, say for in. Cool. Okay, so that's that kind of evaluated. And now it says show this thing here. And you know, classic step question things is look at this x dx. We saw that earlier in the question. Don't forget that the last time you saw an x dx, they asked you to do this with it. So let's just do that again. And now let's wonder what on earth we're supposed to do with this. Well, I guess this is the biggest hint you have is what the answer looks like. The answer looks like a thing plus another thing cubed plus another thing to the power 4 and so on. Is there a e to the expression that does that? I think Taylor says there is. I think Taylor says that there's something that looks a bit like this. So we could consider writing e to the x log x, just replace x with x log x, and we could write it out like this, I guess. Is this helpful? Well, immediately as soon as you write it down, you think, yes, it is, because we have in the previous page, you know, think about this. This is just integral of 1 is easy. Integral of x log x, integral of x squared log x squared, integral of x cubed log x cubed. The constants don't matter. And if we go to the previous page, we just evaluated integrals that look exactly like that. Here, m and m are different, but it wouldn't matter if they were the same, right? That's fine. We can just replace m with n, and this would be all good to go. So I think this is all fantastic. Let's go back to this result here. And again, I've replaced that m with an n here to come up with this result. And let's just evaluate these one by one, right, all the way along the line. So I've run out of space, so I'll continue here. This integral is obviously just 1. Now this one here, we have to put in n is 1 to this result here. So we have minus 1 to the 1 times 1 over 2 to the 2 times 1 factorial. So that's there. Next one, when n is 2, is minus 1 to the 2 times 1 over 3 to the 3 times 2 factorial. And then if we just write out the nth one as well, just replacing this thing here with the nth. Now this front term here, I forgot to mention, of course, that comes from Taylor, right? 1 over 2 factorial, 1 over 3 factorial, whatever power of x or whatever it is that we have, that's going to be the front coefficient of the Taylor series, which is fantastic because that cancels with the n factorial that you have from this expression down here. And then, of course, all that the minus 1s are doing is just going plus, minus, plus, minus, plus, minus all the time. And all these are doing is it's the same number on the bottom of the denominator to some same number power. So this is just 1/2 to the square, 1/3 cubed, 1/4 to the power 4, and 1n over n to the power n, and so on. And it's just going to go plus minus. And I think that's enough justification to just say, therefore, that this whole thing is the answer. So, okay, the second question in this video, and it's the fourth question from the mixed pure booklet, step 3 booklet, is this one here, all about shine and coches. Now, I only know the trick that I'm about to show because it came up in the Hyperbolics booklet a couple of times. This is why doing step questions is important to getting better at step questions. You can write shine like this, and then you can just spot, kind of quite beautifully after the 2's cancel, that 2 numbers that times to make minus 1 and adds to make this thing are just these 2 things, one with a minus, one with a plus. And so therefore we can just write x is this and x is this. That exact thing came up before, but it's very quick if you've seen it. You can use the formula, of course, and everything works out okay, but this is just quite a nice little fast method for that. Now, what kind of equation are we looking at here? Because it's very tempting to say that it's a differential equation, and it sort of is, but more importantly, it's a quadratic equation. It's just the equation that we just saw with dy by dx replacing u. But of course, that means that the solutions are the same as long as dy by dx replaces u. So I think these are just instantly the 2 solutions now. And we can integrate both sides of this to get this and to get this. And now which one of these is right? Because it says find the solution. So which of these is right? Well, if we put in the initial conditions, here we end up with c is 1. However, dy by dx is not bigger than 0 at x is 0. dy by dx is minus 1 at x equals 0. So this just doesn't work. Whereas this one ends up working because this is positive at x equals 0, which is good. And so we end up with this being the one that we actually wanted. And yeah, Cool. So that's the first part done. And actually, we haven't got that far to go. We've got a slightly more difficult one to do here. I really wanted to find a corresponding solution, easy factorization solution to this equation, like we did the first one. But I couldn't quite find it. So you just bust out the formula, right? This is a quadratic in dy by dx. So therefore, you can just bust out the quadratic formula with dy by dx equals the other stuff. So this is the a. Sine of y is just the a terms. That's gone there and there. This is the b, so that's minus b, and that's b squared. And this is the c. It doesn't matter that they're not constants. That quadratic formula never requires that. We can just write it in like this. Now, of course, we can factorize out the 4 and root it to make a 2, and then all the 2's will cancel. And you'll be left with a 1 plus sine squared in this root here, which is, of course, cosh squared, which roots, of course, down to cosh. So we end up here. And now this, again, it's a differential equation to solve. It's more difficult because of the y's here. But if we times over my sine and divide by this top row here, we can at least try and separate this and then integrate both sides like this. And this actually isn't hard to integrate because cosh differentiates to sine. So this integrates to just log of the denominator. Now, if that's a plus cosh, then it's fine. You just have a plus log. But if it's a minus cosh, then minus cosh would differentiate to minus, and you'd end up with needing a minus here to compensate for that. X obviously integrates, 1 integrates to x plus c. Now the problem here is that, like, okay, so cosh is this. When you put in y is 0 and x is 0, when you put in y is 0 to here, just to demonstrate, you get 1 plus 1 over 2 is 1, so that becomes a 1. But neither of these can be evaluated, which is irritating. Minus 1 plus 1 is 0, log 0 we can't do, and we can't do log of minus 2 either. I don't think would have spotted this little trick here. I don't know why I've written that again pointlessly. But on the next slide here, down here, what we can do is we can play a nice little trick, which is before integrating this, let's just pull out a plus minus like this. And we can swap the denominator over like this. Now, just to check this works, if we're using the plus sign, then this becomes a cosh y minus 1, which is this term, the top row of this one here. And if we're using the minus, we can put the minus in the denominator only, and this makes a minus cosh. And then we can have a plus, but the minus makes it minus anyway, so it's minus cosh minus 1, which is likewise the bottom row of this term here. So we're allowed to do this, but the reason it works is because now when we integrate, we end up with this exclusively because cosh differentiates straight to sine, so there's no extra plus minus, just the one that we've already fabricated. And now we can evaluate this at y equals 0 because we either get 1 minus 1, which we can't do, or 1 plus 1, which we can do. There was probably a better way of doing that, I would guess. I don't know. But in any case, we eventually end up with, like I said, we can't do 1 minus 1 in here. So we choose the bottom row, which is minus log of 2. And that will be our C for this to be this will end up being our solution here. Now, we can probably write this. It wants us to write like this, so we just need to do a little bit of very easy work here. I can't even bother to talk about this. You can tidy this up because it's probably a good idea to. And of course you can, this is just 2, so we can write it like this. So that's probably the most sensible thing to do with it. Then it says show that the asymptotes are this. Now, asymptotes are essentially just things that happen when you send x and y to infinity. Like it's just what is the curve essentially behaving as when you send x and y to infinity. Now the thing is, we can't send x to infinity because cosh of y, if you know what the cosh graph looks like, it's just a U shape that minimum at 0, 1. So it's always bigger than 1 or equal to, which means this is always bigger than or equal to 1. Which means if we add 1 divided by 2, we can tell that x is going to have to be negative. Think about the e to the minus x graph. It goes this way, right? It's the exponential, but just flipped from the y-axis. So if it's bigger than 1, then x is over on the negative space. So x is this. So we're actually sending x to negative infinity. And this is just the expression with cosh y written as it kind of is. So it's just this expression here and there as well. So now let's send x to negative infinity and y to infinity first, I guess, to hopefully get a solution. Now, when we send y to infinity, this term is going to disappear because e to the minus something just becomes 0. And when we send x to negative infinity, this term is going to matter because it's going to get really, really big. This term essentially isn't because it's just taking away 1. So as we send them both to those two things, this equation essentially becomes this. We can double this, and then we can take logs of both sides, of course. And then we can separate this out to log 4 plus log this thing here. and then we can cancel this and end up with a minus x, and that'll be our first one. The other one comes from sending x to negative infinity, because that's the only thing we can send it to, but then sending y to negative infinity as well. And very similar things happen, except this term now doesn't exist, whereas this one does now matter because you have e to the minus minus. So this term actually matters, so we keep it. This term still matters like it did before, and a very similar thing happens, except you've just got a minus to deal with at the end. And of course, these two things can be combined and written like this in a sensible way. And that's the whole question done. Thanks for watching.